All right, so how you guys doing today?
Good.
Perfect. I'm good. Thank you. All right, so once again, please make sure you guys keep watching the videos on YouTube channel so you can follow with the all the lecture in class and so forth in the future. Okay. So last time we've been talking about the organic compounds. Why it's so special about carbon and carbon, carbon and hydrogen, what kind of bond they can make, how does S and P orbital be used, and so forth. Okay, so maybe we can try to apply those knowledge to certain compounds. Okay, so we can try to make some compounds. Looks like this one. Okay, so if you have this certain type of a compounds over here, this is, by the way, as I mentioned last time, in kind of a skeleton structure, meaning you see there's all the drawing, but you don't see the carbon and you don't see the hydrogen. So that's the problem. So what we're gonna do once again is when you look at this skeleton structure, which we'll use a lot of time. So make sure you guys know how to analyze the compounds in this structure, and we can move on to how we can do the reactions and mechanism from the compound. So the point is, if you look at all the dots or the ends or the corner, this is where you can find the carbon. So I don't show you carbon or hydrogen, but you can just simply go, oh, here's a carbon, here's a carbon, here's a carbon, 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 carbon. Okay. So, oh, sorry, carbon over here. Okay. Obviously, you see the oxygen over here, which is has to be there because we only imply the carbon and hydrogen in this skeleton. So that means we have one. Yeah.
Dr. Cho,
Yeah.
the bottom right,
Mhm.
is that a O or a C?
A C. Yeah.
Okay.
So whenever you don't see any elements, it's a carbon. Okay. Okay. In the corner. So it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now you know. Oh, there are 10 carbons. Okay. Perfect. And then another thing you really need to know is pretty much this one. The carbon should have 4 bonding unless there is a double or triple bond. Okay. I'll show you how we can do this using this one over here. So now you have a carbon over here, but it has only 1 bond to another carbon here, meaning there are 3 hydrogen implied as well. You just don't see it there, but it's there, because carbon should have 4. Because the carbon is once again group 4 element, it should have 4 single bond or to be saturated. So you have 1 over here, but 3 is missing, meaning there are 3 implied hydrogen. Okay. Makes sense, right? Makes sense? Okay, good. So this is a bit tricky. So if this is the 2 carbons making a double bond over here. So for this one, I suggest you to do this one. If you try to circle this carbon over here, it has 1, 2, 3, and 4. So you can count the double bond as 2 bonds. I mean, it's not 2 bonds, but when you count the possible numbers of the hydrogen on it, you can count as 2. Makes sense, right? It's not 2 bonds literally, but for this carbon-wise, there's 1, 2, 3, and 4. So you can count them as kind of a 2 bonds. So it can be 1, 2, 3, 4. Meaning it's already full. Okay? So there's no hydrogen implied there. This is already done. Okay? So same thing over here, but it will be 1 and 2. So you kind of consider them as like a 2 bonds already there, but we still have another 2, meaning there's a 2 hydrogen implied there. That carbon. Makes sense, right? Okay, good. So maybe can you guys do this one? If you look at the this carbon over here, it has 1, 2, 3 already, right? How many hydrogen will be implied there in that carbon? 1. Perfect. There you go. There you go. Perfect. So there will be 1 hydrogen, 2, and 3. So this one is 1, 2, 3, and 4. Okay. Saying when you look at this carbon here, it will be 1, 2, 3, 4. So you need 1 hydrogen there. Okay. This is also same thing as this one, right? There will be 3. Okay. And this carbon has 1, 2, 3, 4. So no hydrogen needed there. Okay? And we'll be here, will be 1, 2, 3, 4. No hydrogen will be there. How about this one? 1, 2. So it will be how many hydrogen? 2. 2. Perfect. Perfect. So we're done. Okay? So whenever you do this, you can try to count the hydrogen now. So it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. Okay? So now you have 14 hydrogen. And just only thing that is not implied in the compound is the one is not carbon and hydrogen, which is oxygen there. There's 1 oxygen over here. Okay? So you find out, even though you're just looking at the skeleton structure, you'll be able to know how many carbons will be there and how many hydrogens are there, and they're just simply implied in this structure. Okay? So this is simply, you just need to know, this one is the only thing you have to know. But additionally to this one, if there's a double bond, just count as 2. If there's a triple bond, just count as 3. It's not really 3 bonds, but only for you counting the numbers of carbon and hydrogen, you can do it that way. It's okay. Makes sense, right? Okay. So this is one thing you can do for anything. Okay. So you can do this one in this way. That's fine. And also sometimes you have to do this to double check. But there's easier way to do this is this one. So you just count the 1, 2, 3, 4, 10, right? So you know there's 10 for sure. But counting the hydrogen is sometimes very time consuming. Okay? So here's a certain rule I can tell you so you can use it easily. Do you see the 2 double bonds over here, right? 2 double bonds over here, right? So if you see 1 double bonds, do -2. If you see the 2 double bonds, do -4. Meaning each like double bond, meaning loss of 2 hydrogen on the compounds. Okay, so if it's all single bond, for sure you're gonna follow the CnH2n plus 2. You guys remember this one, right? Okay, so if there is a 10, theoretically speaking, you can have possibly at max 22 hydrogen on it. Okay, but the problem is you have 1 and 2 double bonds, so you're losing 4 hydrogen already. Okay, but the thing is you have a ring structure. Okay, ring structure, meaning if it's a linear, the terminal carbons will have a 3 hydrogen, right? Because those carbons at the terminal position will have a 3 hydrogen because only 1 bond, right? 1 here. So in the middle we'll have 2, right? This is 1, 2, 3, 4. 1, 2, 3, 4. So there's 3 hydrogens. But the ring structure is like they're connecting these 2, meaning they will lose the additional 2 hydrogen on 1 on each, because they are going to be in the ring structure. They only need a 2 hydrogen on here to make ring. So if you see also the ring structure, so if you see the double bonds, do the -2. If you also see the ring structure, if it's the, doesn't matter what kind of ring structure, you can do, we call this actually cyclohexane, but we'll do it. Anyway, so the -2, okay, so we have a one ring structure, also you have a -2. And also you have a double bond on this carbon to the oxygen, meaning what? If there's no oxygen, for example, you would have 2 hydrogen instead of oxygen, right? Okay, so that also do -2. So then it will make 14. So this is easier way. But once again, you can always double check if you're in the right compound chemical formula by doing the previous way. But if you don't have much time, just know what that rule is.
Dr. Cho,
Go.
I understand where you got the -2s, but
Mhm.
why is the other one -4 again?
Oh, double bond.
Double bond?
Yeah.
But there's 2 double bonds.
Yeah.
Isn't there?
Perfect.
So why is one -4 and one -2?
Oh, so you have not just one double bond, but 2, right?
Oh, okay, so that's
So
why
I
it's
double the -2. This is come from. So this is a double bond thing. This is a ring thing. Oh, and this is for the oxygen thing. So this is kind of easier way to calculate the numbers of hydrogen. That was a very good question. But it makes sense though, right? So you can always do either way, but this might be sometimes helpful for saving your time. So this is pretty much really good, what can I say? The techniques you need to know before you move on to any chemical reactions. Because you don't even know where the carbon and hydrogen is, you definitely have a hard time why is it happening this way and this way. Okay. Makes sense, right?
Okay, so if it's
Yeah.
like open-ended on both sides, that
Mhm.
means it's a ring structure,
Open-end in the
or
ring structure.
It doesn't. I don't. How do you know that's ring structure? What gives it away
Oh,
as ring
because
structure?
it gives you the ring structure.
Okay.
Yeah.
Okay.
Is it no?
I'm just
no?
confused.
Oh, is it good? Okay. But makes sense, right?
Yeah.
Okay. So, because like I said, if it's linear, I can draw it again. If it's linear, like maybe you have a hexane. Well, we're gonna do this too. Don't worry. But like I said, terminal carbons will have 3 hydrogen because this terminal carbon can have only 1 carbon-carbon bond, but the carbon should have 4. That's why we actually can see implied 3 hydrogens there. But if you do make a ring structure, those where carbon are linked.
Okay, I understand
Oh, you got it.
now. I was just confused.
Oh, it's okay.
Thank you.
Oh, no problem. That's a good question. So, that makes sense, right? Can I move on? Okay. Just let me know anytime, because this is a really important part of your the organic chemistry review. Okay. So we'll move on to the bondings too. Okay. So whenever you have certain types of the bond, obviously made in the compounds, you're going to see some regular covalent bonds. Obviously, this is the type of bond you will see most of the time. But the tricky part is you have some polar covalent bonds. Okay, and you might heard this so many times in previous the chemistry course, ionic bond too. So I'm not gonna do much of the very detailed information because it's kind of sometimes very arbitrary. Because here's the thing, you know how we interpret the electron in the compounds is we use the wave function. You guys remember this one, right? Wave function. So that means the electron is for sure is a matter. It's the smallest matter you can think of. But whenever you do the orbital, make a bond kind of thing, we more focus on the wave function. Meaning the Schrodinger was focused on using wave property of the electron to make this the type of chemical bond explanation. And whenever you modify the wave functions, you're actually going to see how those two elements will make a bond and so forth. So it's kind of ironical that you do acknowledge that the electron is matter, but whenever you got into the bonding, you start thinking about the wave property of the electron all of a sudden. Okay, so this is type of reason why you may see a little bit of a arbitrary thing over here. So I'm not going to go into much detail, but only thing you really have to know is the orbital is just the 3D map where you can find the electron by chance, you don't have to locate the exact location of the electron. You just need to know what might be the probability of finding electron and somewhere on the nucleus. The nucleus for sure, but the elements. But it's the higher is where you can see the covalent bonds. That's all you need to know from before we start. Okay, makes sense, right? So it confuses sometimes. If you do, you can find me in the office, so I can help you to understand. But it takes quite a long time, so I'll skip that one. So the only thing you really have to know about the covalent bond is this one. So sometimes it's really hard to tell if this is going to be ionic bonds or covalent bonds or polar covalent bonds and so forth. We're gonna use electronegativity in the Pauling units. Okay. So in the Pauling units, the maximum that we can get is 4. Obviously from maybe somewhat close to 0, but very small number to the number 4. So the highest one that has is the fluorine. So this is because except the noble gas, if in the periodic table, that is the smallest one and the top right corner. So this is the kind of our standard set by Pauling as a maximum number, which is 4 in this case. So it's not going to be on the exam, but I'll just explain. So if it's from 0 to 0.5, it's just regular non-polar covalent. It's just the regular covalent bonds. If it's somewhere between, including 0.5 and I think 0.5 or some, no, it's about 2 actually. 2, then it's going to be somewhat we call polar covalent bonds over here. Okay, if it's bigger than 2, okay, if it's bigger than 2, we call that ionic bonds. So the major difference between ionic bond and the covalent bond is the covalent bond is just try to set a certain designated space where they can find the common ground to share their electrons from one of each and the element in the bonding. So those are the kind of try to cooperate together, find the common ground to store the electrons. But the ionic bond is more like their gap between these two is so large, so they can actually do that. But instead, the one dominant element will just get the electron, because they're so powerful compared to the other one. So they will become either just one that get lost to electron is positive, the one gets just pulled the electron toward so strongly become negative. So those interactions between these two will be basically Coulomb's law. You guys know plus and minus charge will attract each other, right? So even though it's even bigger gap, this is normally weaker than covalent bond, because covalent bond is actually going to find a very good space to share the electron together. Okay, I hope that makes sense. Is it good? Okay. So you don't have to know about all the numbers. Obviously, it's just because you see some like a very ionic, like very polar covalent bond. Sometimes you name it. So the only thing I want you to know from this review before we are hitting the actual organic chemistry is this one. So whenever you look at the covalent bond, one extreme example would be this one. So this is very close to the ionic bond, but yet it's not ionic bond. So this is still covalent bonds. Okay, this is very still covalent bonds, but meaning this is a bit more electronegative than hydrogen for sure. So if you redraw this one again, this is the space they agree that both hydrogen and fluorine agree to share their electron one each other, make a pair of electron. This is there, but because of the electronegativity, this is more electronegative than this one. If you split this covalent bond in half, like equally 50%, 50 left and right. Once again, you're going to see, so the chance to find the electrons in the right half of your covalent bond will be higher than the left half. Because this is more electronegative, means they have a stronger power or force or their ability to attract the electron here. But still, electrons are here too. So if you look at this as a material view, it's kind of confusing. Because what do you mean? It's electron. So some diagram in your textbook says this one. This is not particularly right description because it doesn't mean that electrons always stay near the fluorine. No, it means you may have a higher chance to find the standing wave, which is electron in this wave function, around this one. But you see the electrons over here as well, but just lower chance, that's all. So that's kind of confused if you look at the picture like this one. But just only thing you need to remember is the polar covalent bond for your exam or quiz. It's simply you're gonna have a higher chance to find the electron near to the fluorine because of this. Okay. Does it make sense? Oh, you guys are doing great. That's very nice. Okay, so this is why sometimes you need to think about the dipole moments of the molecule, and particularly just certain distance between the two different charges. What's the dipole moment thing over here? Only thing you have to know for the dipole moment thing, I'm not gonna put the mathematical problem about the dipole moments. You guys remember this is I think Jenkin 2. Just briefly explain. Like, you know. You guys remember this? The mu equal to charge times distance. Is it the Jenkin 2? So I'm not going to do this. Don't worry about it. I'm just showing you. This is the one you need to consider about two different charges and what distance will make how much of the dipole moments over there. Especially they're in the unit of actually the units is capital T. But don't worry about this one. The only thing you really have to know about this one. So if you look at those in the textbook, don't worry about doing the calculation. The only thing you really have to know is whenever you have certain type of compounds like maybe I can give you other things. So the organic compounds, okay? This is better. This is organic compound. It's a methanol, right? Methanol. We'll get there how to name it. But anyway, so this is organic compound, right? And you can assume all the center of the elements are what? Nucleus, which is a positive charge. That's for sure, right? And those electrons are in a bond. This is our actually non-covalent bond. So they're quite nicely like distributed over here. Here not so much because it's going to the oxygen is a bit more electronegative than carbon. This is some out there, but the major force that will actually make a dipole moment here, it will be lone pair. So this is the only thing you have to remember. Whenever you look at the compounds, make sure how many bonds are made on each element in the compounds, and that will actually tell you where you can find there might be some lone pair, 1 or 2 or 3. You can basically get it from there. So let's check this out from there. Okay, so you have a carbon here. So 1, 2, 3, 2 oxygen. So it's now fully saturated, and oxygen over here is this one single bond to the hydrogen over here. So the carbon-wise is good. Hydrogen 1, 1, 1, because hydrogen is group 1. That's fine. This is also good. But if you look at the oxygen right here, this is a group 6 element, right? This is group 6. So that means they're going to have a 1 and 2, 1 and 2, but they still need to have a 4 more. So I'm gonna fill the 4 more electrons on the top of it. Okay, and remember that those electrons are always going to be exist in a pair. So you're gonna pair them in 2. Okay, so we made 2 pairs of electrons are not used for bonding. We call them lone pairs. I think you guys remember this. So the charge difference between these electrons and the nucleus mostly coming from this one, but 2 more onto this way. Because the, I don't know if you guys watched the video on one day. So this is, technically speaking, looks like a band. Oh, sorry. This looks like a band in the molecular structure. But because of these 2 lone pair, electron domain structure will be perfect. Yes, there you go. Because you consider this lone pair as also like a bond in the electron domain structure. Meaning they're actually sticking up from this side and this side. If this is an axial, if it goes on here, it should, this is axial, right? And this is go here, here, and here. This is all what? I mean, here will be smaller than 1 to 9.5. I figured, but anyway, there will be some like a less, like a 1 to 9 kind of degree. It's a little less, a little wider over here. But that means they're going to have a lone pair on this way. So this is kind of showing in this direction. Then overall, in the vector sum, will go into this direction over here. Okay. So the on your exam on the quiz, whenever I ask you the direction of the dipole moments, you just need to find the lone pair. Okay, you just need to find the lone pair, and how would the nuclear positive charge will make a dipole moment from the most abundant electron finding location, which is lone pair, to there, and your arrow always heading to where is more negative. So let me give you one more example. So I know this is kind of it's not organic compounds. In this way, you have a dipole moment just simply going in this way, because you have a lone pairs on the side, but the sum of vector of the dipole moments will be still heading in this way, because the here to here to here will be this one. Okay, so once again, basically, only thing you really need to know is how you can find the lone pair on each element. If you do find one, just make sure that arrow will heading to where you can find the lone pair more, because this is where you have a more dramatic change or gap between positive charge, which is your nucleus, to the electrons. Most abundant electron region, there is no space or lone pair. That's all you need to know.
So you want us to draw an arrow?
You don't have. I think I'll show you.
How would you state the answer? Like.
Oh, so I haven't made the exam question yet, but I think I will not show you the lone pair, but I think you can find them.
But like you're asking for the dipole moment and what direction?
You can maybe draw it. Maybe I don't know. I didn't make the exam yet, but yeah. But maybe either you can draw it. Maybe I can show you the picture and you can pick the right one. I think that's easier that way, right? Yeah. So that's pretty much it. But you do understand though, right, why it's happening this way? Because the electron, the nucleus, this is the way we have the dipole moments. So the lone pair will have a definitely critical role on this part of the topic. Okay. So maybe on the exam or the quiz, I'll probably just give you the picture. So it's like a multiple choice. So you can just pick the one. So maybe you pick where you can find the lone pair. You see the arrow heading that to the lone pair. That's the answer. Perfect. I think you guys are doing so great so far. I mean, it's just kind of a lot of things I'm covering today. But if you do have any question or other thing, just let me know. So next one, so next one is the, okay, I'll do a little more and we'll have an extra credit thing, okay? So if you look at the, okay, so if you look at the certain type of the compounds, it looks like this one. You can try to put the forward charge is what we call. Okay, so forward charge is the defined by the how many electrons you have, but from the what you're supposed to have. So meaning if you have like a 10 electrons should be around your compound, but if you have 11, your forward charge of the compound will be -1 because you have 1 extra electrons, right? But if you have maybe 9 instead of 10, meaning you're losing 1 electron you're supposed to have, so they will become positively charged. So normally what we do is we put the bracket on here, so you can have an overall charge on the compounds, okay? But what you can do sometimes too is you can try to get the forward charge of each element. So if you can do that one, you actually tell, if I point the one element in the compounds, I'll show you also the numbers of the lone pair as well. You can actually tell me which carbon or which sulfur or oxygen will carry what charge, and then overall what makes how many charge on overall compounds. So maybe I'll draw it more this way so you can more easily look at it. Okay, so if you have this type of compound over here, what I normally do, if you go to a textbook that says a certain calculation you can do, like numbers of bonding divided by 2 would be number of your electrons that are on the compound. But I think this is faster. This is my own way to do it. Hopefully you can get this one too. This is something we already did so many times, but let's do it again. So this is carbon, right? And this is group 4. Okay, this is group 4. So meaning you should have either 4 single bond, 1 double bond, 2 single bond, triple bond, 1 single bond, so just try to circle the elements around it, okay? And you have count all the dots in the tip of the line, that'll be 4, meaning each electrons, each valence electron available for or used for bondings. So it'll be 1, 2, 3, and 4, okay? So now it's happy, okay? Meaning this carbon should have 0 formal charge over there because they're happy now with the 4 electrons around it. Well, we obviously will share to each hydrogen and the sulfur, but for now around the carbon here is 4. There's a 0 charge over there because it should have 4, but it has 4. Okay. Same thing here, 0 charge. So obviously, for hydrogen, if you circle this one, you only have 1 dot here in the tip, but that's okay because hydrogen is group 1, so it's also happy, so there's no charge on hydrogen either. The tricky part is these 2. Okay, so central sulfur is, you look at the 1, 2, 3, okay, and then you count the lone pair all. Okay, so it'll be 1, 2, 3, 4, 5. This lone pair is a pair of electrons, there'll be 2 electrons there. So sulfur has now 5 electrons, but sulfur is group what elements? 6, perfect. So meaning it should have a 6. It only has 5 now at the moment. So it should be positively charged. 1 plus charge. Okay? Over here. But vice versa, in oxygen here, it has, so there'll be 1 bond, 2, right? So 1 bond, so it'll be 1, 2, 3, 4, 5, 6, 7, because there's 3 lone pairs, so it makes 6 electrons, but 1 from the bonding 2. So it adds 7 electrons, but oxygen is also group 6. So it should have 6, but it now has 7. So it has more than what we need, what they need, I mean the oxygen needs. So that's the one more electron, but electron is negatively charged, so it will have a one negative charge on oxygen. So in overall, there is no formal charge because it's plus and minus, but for each individual element in your compound may carry different charge. But just formal charge for the whole compound, maybe just don't say it specifically, but you can actually do it by looking at how many lone pairs on the specific elements and how many bonds are made, and just try to count them as well over there. Okay? Do you want to do one more? Let's do one more. Okay, let's do one more and then let's do extra credit. So let's do the water again. So if this is the case, if I give you this one, okay, this one will have only 1. This one is only 1. That's good. But how about the oxygen? Can you guys tell me? So oxygen is group 6. You count each dots and the lone pair, how many are there? 6. Perfect. So what's the formal charge on this one? 0. Perfect. So in total, 0 as well, right? Okay. Okay. So if that is the case, sometimes what you normally see is this one in the organic. So R means any carbon alkyl group. We're gonna do that later, but just you don't have to worry about this one. But specifically for this one, what's the charge now? It'll be 1, 2, 3, 4, 5, 6, 7. So it'll be 1 negative charge. So you'll see this a lot in the organic chemistry. So please remember this one, because the oxygen is, once again, where is the oxygen? It's on the top right corner, right? Meaning it's quite electronegative. So electron is the one in your compound will try to carry all the negative charge rather than other elements like carbon and hydrogen for sure. So you'll see this one a lot, whatever they attach to what organic compound attached to it. Most of the time, the oxygen will be the one who will carry the extra negative charge if there is one. Makes sense, right? We good? Perfect. I think that's pretty much for today. So I'll stop here, but